So that's another thing. If you want me to send you the recording of this lecture, we can do that. You can listen to it again. I can send you just the PowerPoint that you could go through again if you like. Okay, so sometimes the videos on here are helpful. Amber, do you think you can see well enough back there without the light on?
I think so.
Okay. All right, so we're going to be getting into now Module 4, and you should start to be a little, understand a little better how my quizzes work, hey girls, and so maybe start to feel hopefully a little better about those. All right? Okay, so last time, I got to do this. Now, we did this. Some of y'all didn't even answer those last questions, the electron configurations. Okay, the good news is you won't really, except for the midterm, maybe a couple questions, you won't really need this much anymore. So that's good if you didn't like them or if you weren't getting them or whatever the deal was. But the deal is, the bad news is that we need it for something. Okay, so we weren't just doing this for fun or because of academic reasons. The electron configuration tells us something, and it tells us something that is fundamental to chemistry. All right, so it's what we need to know about chemistry. Do you remember when I told you chemistry is all about the electrons? Right, it's not about that. What we care about in the nucleus is the mass. So we care that how many protons and neutrons are in there, okay? But we're not going to mess around with them. That's physics. We do not mess around with the nucleus in chemistry unless we're looking at the few radioactive things out there. But what we do mess around with, what we do manipulate, are the electrons. All right, so we need to know which electrons we're messing with. And that's what these electron configurations are doing for us. All right, so we're looking for something, we count these right here at the end, and those somethings we're looking for are known as valence electrons. All right, so here's another picture of them right here. Remember we took it and we could make the abbreviated electron configuration, right? So we all know what that means. Beryllium is helium with a 2s2 on it. So now you can probably picture it in your mind. Start thinking in chemistry, y'all. You can picture in your mind on the periodic chart of the elements. There it is over there to the left, right? S, it's an S2. So it's way over there to the left. Yeah, and if y'all probably need to pull out your periodic element charts because we're going to need to use those today as we go along. All right, so we're looking for something called the valence electrons. Not to be confused with valence. A valence is something that goes in the window, right? But a valence, I think they're spelled exactly the same way. The valence electron is what we're looking for. So I think one of your first blanks in your book right here, let's see. So right there at the top there, electron configurations and the periodic chart. An atom's chemistry is determined by the number of valence electrons it has. You're going to write in that blank valence electrons in that first blank. All right? Use the blank on the periodic chart to determine the number of valence electrons. Okay, you're going to use the columns. You're going to write column in there. So what is the valence electron? It doesn't ask that. Oh, it's asking us to do another, that box. We might be skipping that box. I'm not really sure.
Valence electron.
Yeah, below that box. See where it says valence electron? All right, this is where you're going to write this. The electrons in the farthest orbit from the nucleus, therefore the highest energy level. The farthest orbit from the nucleus. This will come up again in another slide. So if you recall, when I told you about those orbitals, those shells, the p shell, the s shell, the d shell, I mentioned it in terms of energy levels. Okay, so we're looking at this energy level. So we're looking at the highest energy level is going to be the farthest from the nucleus. And sometimes they're all by themselves out there, all right? And they're looking for something. And they're looking for more electrons to have chemistry with. They want to go do chemistry with some. They want to hang out. All right, so here it is running along in its outer orbit right there. It's in the outermost shell, and it's ready to do something. It's ready to socialize, okay? Just like y'all, right? After all this pandemic business. All right, so remember, this is the same thing. If you didn't get that written down, it's right here. It's the farthest orbit from the atom's nucleus. It has the highest energy number. Okay, so maybe, does it say bromine in that box there? All right, you're going to write this down. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5. And does everybody remember this D level? When we get over to that one, we had to drop that number down 1. Do you remember that? Okay, remember what that number is? It's the energy level. So in that middle group, in the D shells, we drop it down an energy level. It has to do with the way the shells are shaped. And that energy level is lower because it actually comes like inside the orbit, if you will, of the other ones. So looking at the big numbers in the front, I can see in this particular atom, it has the highest energy level it has is 4. Do you see them? That 4 refers to the energy level. The electrons in that energy level are the valence electrons. So what tells me electrons? This is energy level, that is electron. That little 2, so the small arrow here, and that 5 right there are referring to the valence electrons. Those are the electrons that are in the farthest orbit from the nucleus. Does that make sense to you? All right, so how many valence electrons do I have? I have 7. 5, 6, 7, right there. Okay, can y'all find bromine on your chart real quick? I'll give you a hint. Look to the right. You see it? What number is it? Say again? 35? Okay, so what do we know about it? If it's number 35, we know it has 35 what?
Protons.
Protons. Protons. There are 4 electrons, yes, but remember we're going to define it with protons. Make sure that definition is protons. But it also has that same number of electrons. But how many valence electrons does it have? 7. Now check it out. I want you to start over at hydrogen, to the left. That row going down is 1. The next one to the next is 2. Now skip the yellow guys in the middle. And then over there now on the green or blue, whatever color that is, we have 3, 4, 5, 6, 7. Where's bromine? Is it in row 7? Yes. What did the little numbers say above your chart right there? Does it say 7 or does it say something weird? 17?
17.
Okay, so you're going to ignore those 10 in the middle right there, and we're going to call that 7. Okay? And how many valence electrons does it have? 7. Now, what's right below beryllium?
Iron.
Guess how many valence electrons it has? 7. Yeah, that's why it's there. That's why the chart is arranged the way it is. All those in their little row have the same number of valence electrons. Pretty cool. So I can ask you, tell me how many valence electrons are in helium. Well, don't do helium, do neon.
8.
Yeah, it's going to be 8. All those guys down that right side are going to be 8. Helium's going to be 2. It's just helium and hydrogen are special in this whole deal right there. So why is this so important? Okay, compare bromine to fluorine, chlorine, iodine. Do we have another one? And now the valence electrons. What is the highest energy level in fluorine? It's 2. So how many valence electrons are in my 2 energy level, 5, 6, 7? Here my highest energy level is 3. How many are in there? 5, 6, 7. Over here, look what I've got. I've got my energy level. Wow, it's going all the way up to 5. 5 is my energy level in iodine. How many do I have? 5, 6, 7. You see, they each have that same number of valence electrons. Do you notice a trend? Yes. Furthermore, I will tell you that these guys, including bromine, all behave similarly. In chemistry, they behave similarly. Okay, so what is chemistry? An atom's chemistry is determined by the number of valence electrons it has. This is review, that was at the top. Use the column number on the periodic chart to determine the number of valence electrons. And this all fits together to determine how many atoms of different elements, how atoms of different elements react with one another. All right, so that's reviewing those top blanks we filled in, yes? So here you can see, for instance, boron has 3 valence electrons. You could have probably told me that if you found boron, it's probably in that 3rd column, yes? Is it over in the 3rd column? Yeah. Silicon has 4, so it must be in the 4th column. Antimony, that's a good one. Antimony, its symbol is SB, has 5. 1, 2, 3, 4, 5. And those are the ones, these dark colored electrons here on this picture are the ones that are ready to do chemistry. Okay, ready and willing to do chemistry. So here are our groups. Now notice right here on group 1A, I have hydrogen with a little dot next to it. How many dots do I have next to it? 1. And lithium has 1 dot, sodium has 1 dot, potassium has 1 dot, and all the way down row 1. On 2, I've got 2 dots all the way down. 3, I've got 3 dots, 4, 5, 6, 7, and 8. Notice helium has 2, and then the rest of them are going to have the 8. 2, 4, 6, 8. You see that? Okay. Now something interesting, when you have this, look at neon. When you have that 1, 2, 3, 4, 5, 6, 7, 8 dots around it like that, neon is full. Neon is full. All right, because it has 8 dots. And that's what everyone else wants. Like, for instance, fluorine has 7 valence electrons, 7 dots. All it needs is just one more, and it would be happy. Finally, fluorine could be happy if it could just get that one more electron. So guess what? It's going to make a deal. It's going to make a deal with something else on the chart that's got 1 electron to offer it. Oftentimes it ends up making a deal with itself and joins up as a group together. Yeah, we'll see how that happens. Okay, which brings us to the octet rule. All right, the octet rule says most atoms strive to attain 8 valence electrons, to have those 2, 4, 6, 8 dots around it like that. Most atoms, notice it says most, we can't say all because you can never really say all. Most atoms strive to attain 8 valence electrons. The exception, of course, would be hydrogen. Hydrogen who wants to have 2, like helium. Okay, so hydrogen only wants 2. There are other exceptions, but chemical reactions occur because atoms are trying to achieve 8 valence electrons, known as the ideal configuration. It also, when they have it like that, there's nothing unsteady about it all. When it's all full out there, there's nothing missing, so it feels steady and good, and it's got low energy level. It can just be lazy now. It can just be lazy. And sometimes it goes through a pretty amazing reaction to get to this state, but that's what chemistry is. Some chemistry reactions are dramatic, some are boring. All right, so this same thing. Atoms tend to gain, lose, or share 1 or more of their valence electrons to achieve a filled outer electron shell. That's the octet rule. 8. Striving for 8 is great. Okay? Everybody wants to be noble. The king. That far right column, helium, neon, argon. What comes next?
Yeah, argon.
All those down, they all have 8 valence electrons. They're in group 8, right? You know what we call those guys? We call those guys the noble gases. Noble. Everyone wants to look like the king. And remember those noble gases, you may know that we use neon, right? Neon, for neon lights. I thought these lights were, we call them fluorescent lights, but I thought there were argon in there, but argon looks like it glows purple. All right, so guess what about those guys over there, those noble gases over there? They tend to not do any chemistry. Because guess what? They don't have anything to share. They're happy the way they are. They're like, no, leave me alone. Now, does that mean we can never do chemistry with them? Well, we can force them. We can put some energy in there and force them to do something. But for the most part, they're what we call inert. They don't do any chemistry. All right, so we don't want to use those to react with anything because they're full already. So remember, our goal in chemistry is to react things together so that everybody ends up with 8 valence electrons. And so if they already have it, they don't need to do any chemistry. They don't need anybody else. They're noble. Which brings us to those dots I was showing you earlier in that thing right there. We call these the Lewis dot structures. All right, and to do this right, we're going to have to use your periodic chart of the elements, which you should have out already, yes? And you can see, this is oxygen. Let's count our dots. 1, 2, 3, 4, 5, 6. Is it in group 6 on your chart? Okay, so it has 6 valence electrons. So notice I want to have 2 at the top, 2 at the side, 2 at the bottom, 2 at the other side. So I have a spot available right here on the bottom for another electron to come in, yes? And I have a spot right here for an electron to come in. Can you think of something that might come in with 1 electron and share? Right there.
Hydrogen.
So if I have hydrogen and I put 2 hydrogens in, what do I end up with? Water, right? Beautiful, right? It's beautiful. It's a beautiful arrangement that is made between oxygen and hydrogen, and they form water. All right, so that's one of the most beautiful out there, although the Lewis structure can get a little hairy. All right, so this notation was developed by this guy, Gilbert Lewis. He was at the University of California, Berkeley in the early 1900s. They're also known as electron dot figures. But it kind of takes away the credit from Mr. Lewis or Professor Lewis, so we like to give it to Professor Lewis there. It assembles the valence electrons of an element in an electron dot diagram. That looks something like that. So take a look at lithium. It's got one dot, so you know where to go. Where is it? Group 1, right? So there's one valence electron right there. Do you think it would have liked to share with oxygen? Sure. Yeah, L2O, like 2 lithiums and an oxygen. I don't know what that is, but. All right, so we're going to try a few right here, which is why you need your chart. So let's see. Find beryllium on your chart. What group is it in?
2.
Okay, so how many dots does it have? I'm going to come over here a little bit and grab this. Okay, so beryllium, Be, it has 2. Now, something about the way you draw the dots, there's a little bit of a personality, so we're going to kind of go with what the book wants to do. And what we want to do is we don't want to just put 2 dots right here. Okay? That indicates that side is full. All right? So what we're going to do is we want to say 1, 2, put it down there. Okay, not right next to it. So then boron, what group is boron in?
3.
Okay, so we're going to say 1, 2, 3. All right, y'all supposed to be putting dots by them in your book? Go ahead and put those dots by them. Where's carbon? What group? 4. So we're going to say 1, 2, 3, 4. This becomes super important for carbon, the fact that it's got 4 bonding spots. Nitrogen must be 5, yes? So notice what I do with the dot now. I'll put it up here so y'all can all see. Nitrogen, I have 1, 2, 3, 4, and I'm going to bring it down, and that one side's going to have 2 on it now. Okay? And then oxygen, I'll have 1, 2, 3, 4, 5, 6, yes? Yeah. So that leaves me 2 blank spots on there. And then next is neon. We know neon's happy. And neon. 1, 2, 3, 4, 5, 6, 7, 8. So it's got 2 dots on the top, 2 dots on the side, 2 dots on the bottom, 2 dots on the other side. So it's happy. And I think I have those coming up right there. Okay, so see how those dots are arranged. And when we end up with the octet, you can see that they're lined up like a square around it. We're going to try a couple more. Calcium, y'all tell me. How many dots?
2.
Hooray. 1 on top, 1 on the side. I don't know which one's next. Silicon, tell me about silicon. What group?
4.
4. 1, 2, 3, 4. It's going to have similar qualities as carbon, right? Next comes, is that acetine? Did you say 7?
7.
Is it 7? There we go. 1, 2, 3. Is it 6? 1, 2, 3, 4, 5.
It's 7.
It's 7?
Mm-hmm.
Okay, well add 2 dots to mine. And then gallium is 3. Now notice how somebody did the dots kind of weird. So not everybody does their dots the same. It's just we want, like I would have had a second dot here. So AT, did y'all tell me it was 7?
It is 7.
Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2. We need 2 more dots on that one. I apologize for that. I just wasn't paying attention. Okay. Now, keep in mind, still looking at your chart, that we have those things called metals and nonmetals. Remember what delineates those. We have that line that kind of stair steps down. Oh, y'all need this back? Just don't do AT like that. But put 7 around AT. Good, good. See, you're getting hang of it there. That's good. And now you know that those dots, therefore, are going to tell us what kind of chemistry they're going to do. Okay, so we're going to see that. So if astatine is 7, it only needs 1 electron to be full and be happy. Yet one that just has 1, boy howdy, they need to try to get a hold of 7. That's going to be hard to do, so they're going to be more apt to actually give up the 1, to get rid of it. And they'll end up with 8. We'll see that in just a second how that works. Okay, so also remember, this is just a little review right here. Do you remember if something is ionic, if something is ionic, remember what that means? It's going to have a metal and a non-metal, remember that? That's from before? Okay, so if we have an ionic compound, then we are going to see the non-metals are going to try to gain, write that in your blank, are going to try to gain electrons to achieve 8 valence electrons. What do we need, y'all? Y'all are looking confused.
Oh, there's no blank for that. I think.
Yeah, there is.
There is?
Yeah.
Oh, I didn't.
That one I looked up.
Oh, I do have it written down.
Metals try to lose electrons to achieve 0. Now that sounds weird that they want to achieve 0. But the deal is if they get rid of that outer one, then what's going to be left behind? It's going to be a full shell of 8. So they actually are going to achieve 8. They're just going to achieve 8 by losing something rather than gaining something. All right, so metals tend to lose and non-metals tend to gain. And it's because where they are on the chart. It makes sense, right? It makes complete sense. All right, does everybody have those 2 blanks filled in? Okay. So let's talk about a Lewis structure of sodium and chloride. So this will completely explain it all to you right here, okay? So check out sodium. It's in group 1 in your chart, yes? Okay, so it's got that 1 valence electron just hanging out there by itself. Chlorine's in group 7. And so they strike up a deal. Chlorine says to sodium, hey, you've got an electron that if you get rid of, you'll be happy. And if I get it, I'll be happy. Let's be happy together. Okay, so they're gonna get married. This is a proposal, y'all. Okay? So what's going on is literally, sodium says deal and gives this dot and puts it right there in that empty spot for chlorine. Now, but it wasn't free, if you will, because guess what? Sodium has now lost an electron. That's going to do something to sodium. It's going to have one more positive charge in its nucleus with its protons than it has negative charges with electrons because it lost one. So that's going to give it a charge. Okay, a charged atom is called an ion. That's what an ion is. All right, so it's going to give it away, and therefore the sodium is going to have a plus sign next to it, because that plus sign means that it has a charge of plus. Chlorine, by the way, picked up a negative. It's going to have a negative sign right there. The reason this is in brackets like that is just to, in this particular case, to keep those dots kind of not get messy there. We want to keep those dots kind of neat if we can. All right, so now we have a positive charge and a negative charge that are really close to each other. They're going to act like a magnet, and guess what they're going to do? They're going to stick to each other. Okay? That's a type of a bond. It's called an ionic bond. They're bonding together. Okay? So they, are that way. They're that way together. And we can break them apart fairly easily because they're only just like pulling a magnet apart. So that bond is not super, super, super strong, but it is a genuine chemistry bond. They're really the only 2 chemical bonds we'll be looking at today are ionic bonds and covalent bonds. Covalent bonds are a little different. Instead of giving away an electron, they end up sharing an electron. I just put up here for sodium, there's our 1 valence electron right there. All right, so we call these ions, and when we put them together, we put the IDE on the end, so we call it sodium chloride, because that's how we name ionic compounds. We knew that already from module 1 or 2, right? We already knew that. Okay, let's try a harder one. First thing you need to know is that if it's a positively charged ion, we call it a cation, and if it's negatively charged, we call it an anion. So you could, for anion, you can say A negative ion, okay? A negative ion to help you remember. And if you like cats, you think positively about cats, start to think positively about cats. That'll remind you that a cation is a positive charged ion. All right, so I have magnesium and I have fluorine. What group is magnesium in? 2, so it's going to have 2 dots. And what about fluorine? 7. Okay, that sounds like an arrangement right there, doesn't it? So can magnesium give away those 2 dots to fluorine? One of the fluorine gets one and the other fluorine gets the other one? That would work, right? All right, so let's see what happens. So each fluorine's going to get one of the electrons. They're going to gain a negative charge right there. But look what happened to magnesium. It lost 2 electrons. So what is its charge? 2 plus, right? Do you see that? So I have ions now. I have an ion of fluorine, I have an ion of magnesium and I have another ion of fluorine, and they have those opposite charges, therefore they're going to kind of stick together like a magnet, and that's called an ionic bond. So that's not too bad, right? What do you think that one's called? Magnesium fluoride. Magnesium fluoride. Okay. All right, so the main thing on this slide I wanted you to see, so it's MgF2. I wanted you to see that cation and anion are those, anion, sorry, are those names right there. Okay, now, there is a shortcut. This is the good news. All right, so if you look at your chart again, you're going to see that in group A1, this is just, we're looking at the ions and what they want to do. So how are they going to end up? So if group 1 wants to give away an electron, they're going to end up as a +1, yeah? They're going to end up as an ion that's +1. So we have for group 1A, we can just remember it's +1. We're going to end up with those guys being +1. Group 2 is going to be +2. Now it gets a little more difficult in the middle groups because there's, you know, certain numbers right there. So right here, group 3A tends to be 3+, except for boron. Boron will probably, instead of giving up electrons, try to gain some. Group 4A, look, it's -4. Right, -4. That means it's going to gain, it's kind of weird to think, it's going to gain negatives, yes? It's going to gain, now we're only doing that for our carbon and silicon. The rest of them, they don't count. We don't care about them right now. It gets a little more complicated. We're not going to do the complicated ones. We're just going to do the regular old chemistry ones, okay? The ones that generally follow the rules. We're not going to look at the rebels right now. The rebels you pretty much cover in chemistry 2. So if any of y'all are like loving chemistry, eating it up, love chemistry, you may want to take chemistry 2 someday. I don't know who's going to teach it to you because it's not going to be me, all right? I don't like it. All right, group 5A is going to end up typically with a -3. Group 6 with a negative, these last two almost always, a -2. And group 7 is going to be with a -1 right there. All right, so if we looked at it on the chart, oh, by the way, that's on table 4.1 on page 140 of your book. So you can see we have a +1, +2, +3. Look at this one, says plus and -4 on our group here. And then we have -3, -2, -1. And of course, our noble gases don't do anything, right? Because they're inert. They're not going to do chemistry. So over here, remember, we're just going to do carbon and silicon for our, was it our -4? Yeah, for our -4, okay? Some of these other ones might be a +4, but if something like that happens, I'll let you know that, okay? So for now, just remember that group. Carbon, silicon are going to end up with a -4. They're going to gain 4 electrons. All right, so this is the fun part. In general, we found this when naming the compounds, that the ionic ones were easier to name than the covalent ones. And so this is the same as well right here. So if the charges have the same value, then the subscript for each is 1, whichever's 1 is dropped. Okay, so in other words, if I write H2O, I don't have to write H2O1. Okay, I just write H2O. We know there's a O in there because the 1's right there. So the 1 is dropped. 2, if the charges have different numerical values, you drop the plus and minus, switch the numbers, and use them as subscripts. I'm going to illustrate this to you. We're going to watch a little video on this so you understand what's going on right here. What we're doing is we're doing crisscross. We're going to crisscross here. And the chemical formula ratio is always the lowest, so it's sort of like doing the lowest common denominator thing. Always make it the lowest that you can. Instead of 8 and 4, you know, you're going to have 1 and 2, right? So however that goes. Okay, so I'm going to show you an example of it, okay? I don't know if the example is one that's in your book or not. Are y'all having to write down all these words? Mm-hmm. Oh, yikes, okay. Yeah. The most important part is number 2, I think. We're not going to have that little positive and minus anymore. It's going to get a little bit cumbersome there. Okay, how we doing? So these end up kind of being the fun ones. The covalents are a little more difficult. So I like ionic. Okay, so beryllium and chlorine. We're going to try to see if we can react beryllium and chlorine together. Okay, so beryllium is in group 2A, so we're going to say that's going to get a 2 plus. It's going to get rid of 2 negative electrons, yes? Chlorine's in 7A, yes, it definitely wants to take those electrons. Thank you very much, beryllium. I would like to take that. Okay, so here's what I do. I'm gonna put my beryllium with its little 2 plus up there, and my chlorine with its little minus 1 over there, and I'm gonna put those guys together, and then I'm gonna say criss-cross, and I'm gonna end up with BeCl2. So do you see what happened? The 2 from the beryllium went down to the chlorine. Now, if we took this and we saw that we had beryllium has 2 and chlorine has 1, obviously we're going to have 2 chlorines taking 1 from each beryllium. You know, 1 of each beryllium's electrons. Do you see that? So just doing the crisscross, it totally makes sense. So now my chemical formula for beryllium chloride is BeCl2. Kind of fun. You just pull them over like that. Notice my charges are no longer there. My plus and my minuses are no longer there. What about that minus 1? Why don't I have a Be1Cl2? Because Be is already there. It's understood that there's 1 Be, beryllium in there. Do you get it? Yeah? Okay, good. All right. What is the chemical formula for the ionic compound formed by aluminum and sulfur? Aluminum and sulfur. And then what do we call it? All right, so you're going to see your aluminum and your sulfur in your chart. Where? What groups? They're over to the right.
Aluminum is in 3 and sulfur is 6.
3 and 6?
Mm-hmm.
Okay. Let's watch our favorite professor.
In this example, we're going to determine the chemical formula of an ionic compound. Now to do this, we need the periodic chart, so that's why it's here. And I'm only going to show you the first one, because once you see this, it gets pretty easy. All right, we're talking about the ionic compound that forms between aluminum and sulfur. Let's find them both on the table. There's aluminum, and there's sulfur. All right, now let's start with aluminum. So we'll write aluminum, Al, and we have to figure out what charge aluminum is going to take in an ionic compound. Well, it's in group 3A. That means it has 3 electrons. In order to get to the ideal electron configuration, it's got to either lose 3 or gain 5. It'll lose 3, so it becomes Al3+. That's the rule for group 3A. The metals become 3+ in an ionic compound. All right, what about sulfur? Well, sulfur's in group 6A. It's a nonmetal. It wants to gain electrons. The nonmetals in group 6A gain 2 electrons to get to the ideal electron configuration, so they take on a charge of 2-. All right, so we've got Al3+ and S2-. Those are the charges that these elements will take in this ionic compound. Now getting the chemical formula is a snap. We simply switch the charges. The 2- goes to Al, and the 3+ goes to S. We make them subscripts instead of superscripts, and then we get rid of the charges. So the final chemical formula is Al2S3. This is how you'll determine the chemical formula of any ionic compound. Determine what charge the ions take, switch the charges, drop the signs, and you've got the chemical formula.
So what's the name of it?
Aluminum sulfide.
Aluminum sulfide. Yeah, it's ionic. Aluminum sulfide. We add that ID. Okay, there are some exceptions. I don't believe this is in your little lab book there, but it will be in your reading that you read. Okay, so there are some exceptions. Boron, whatever GE is, tin, and lead are all exceptions. Notice where they are on the chart. Are they in the same group? Boron, GE, tin, and lead. Do you find them? They're to the right there somewhere. I think. There will be a Roman numeral to indicate their charge. The deal is they can do one or the other. It depends on the situation. Okay, it depends on their circumstance. So for instance, if I have 10,2 chloride, guess what that's telling me? That's telling me that 10 is plus 2. Chloride we already know is minus 1 because of the rule. We can do this for, so it's SnCl2. We can do it for 10,4. Sometimes 10 is 4. It wants to get rid of 4 electrons. And with chlorine here, we can have SnCl4. So look here, I have SnCl2 and SnCl4. There are two things reacting, and they end up with two different deals. And it has to do with that particular circumstance of when I'm putting these guys together, okay? So, but if this should come up, then I will tell you it's 10,2. 10,2, almost it's Roman numerals. Or 10,4. Backdoor, right? Okay, there we go. So here are common metals that form more than one positive ion. So we have chromium can either +2 or +3. Here they're Roman numerals, 2 or 3. Iron can be 2 or 3. Copper can be 1 or 2. Gold can be 1 or 2. Tin, 2 or 4. And lead, 2 or 4. Okay? So when you're going through that in your book, just remember that's what this was talking about. It's how sometimes that they will do different. They'll have a different ion. Okay. So let's name these. I only have one of those weird ones, part C here. So let's name these. Who can tell me what aluminum oxide looks like? So you're going to find the two on the. This is aluminum and oxygen. Okay. You're going to find their groups and you're going to crisscross. Do you have all these in your book to write down or no? You do on the kind of bottom middle of page 30. You see aluminum oxide with a blank next to it. So you're only going to write it in there. It's going to be ALO. ALO. What are the numbers?
AL3 oxygen 2.
Al2O3. Remember, switch.
Okay.
Switch. Do you see how we got that? Does everybody see how we got that?
No.
Okay. So tell me what group is aluminum in? Find aluminum. 3. So what do we know about group 3? Is it a metal?
Yes.
So what do they want? Oh, it's Al. Okay. So it's in group 3. So what's it want to do? It's going to want to give away 3 electrons. So we have a -3 there, right? And where's our oxygen?
6.
6. And what do we know about group 6? It's going to be +2. Yes?
Yes.
So now we take our 2 from the oxygen, we cross it down to the aluminum, put it down there, 2. Our 3 from the aluminum, cross it down to the oxygen and put it there, Al2O3. Get it?
How do you know how to +2?
Okay, so remember those rules I gave you a second ago? Okay,
Yeah.
let's go back. No. There. Y'all want to get your phones out and take a picture of this line?
Yes.
I will tell you this, that I believe that my way of writing it is easier than table 4.1 on page 140. So if y'all want to take a picture of that, and you can look at it right now as we're going through these, okay? And then remember our little exceptions here. In our group 4, we're only going to be dealing with carbon and silicon unless I tell you something about them. Everybody have that? Remember also, if you want me to send this lecture to you, it'll be a YouTube video. I can do that, okay? Just let me know. All right, does everybody have this that they want? I'm going to go ahead again. That was fun. There's our exceptions. Okay, here we are. We got that one. Now, calcium sulfide. Y'all should be able to do it now. Calcium is in what group?
3.
Okay, what do we know about group 3?
It has 3 positive.
Okay, and then sulfur is in group what?
6.
So what do we know about group 6?
It has -2.
Okay, so can y'all tell me what? Oh, interesting. I might have it wrong on here.
It'd be Al263 or S2.
It's calcium, right? We're talking about calcium and sulfur.
Oh,
We're talking about calcium and sulfur.
Calcium. So
Where is calcium? Okay, what did you say, Priscilla? Okay, so, and remember we're going to go with our lowest common denominator. So Priscilla's saying Ca2S2, is that what you said? Ca2S2. Okay, but we have to, can that be divisible, the two of them?
Yes.
Yes, there we go. CAS. Do we see how we got that?
I was on the wrong one.
Okay, I was about to say, wait a minute, either I've got it really wrong. Okay, now the next one's giving us a little more information. First of all, whenever you see chloride, say, hooray, I always know what chloride's going to be. It's always going to be -1. I always know that. All right, hooray, hooray. But chromium, I don't know unless I tell you, so it's 3. So now you can tell me what's going to happen. Where is chromium? What is its symbol, CR?
Yeah.
It's going to be CrCl something, right?
CrCl3.
Perfect. You see that? Because that 3 just is that where that 3 came from right there. Chloride's 1. It's always 1, -1. So it's always going to bring that 1 down. Does everybody see that? Okay, cool. Potassium nitride. Okay, potassium. We're looking at potassium, that's K, and nitrogen, that's N. So we know where K is, all the way to the left. Nitrogen to the right. Anybody have an answer for me? Somebody said it. K3N. And that's potassium nitride. Aluminum sulfide, didn't we just do that one? Didn't we do aluminum sulfide in an earlier slide? So what do we have?
Al2S3.
ALS3. Where'd you get the 2 from? Sulfur.
No idea.
No idea. Oh, here's a tough one. Cesium nitride. We know the nitrogen. We know where that is. What's our cesium? Is that Ce?
Yes. CS3N.
That is correct. Everybody see how we got that? That N, the N's going to be our 3, right? It's going to come over. I don't know where cesium is.
First column.
Is it number 1? That makes sense. Magnesium oxide. I should pull my chart out, I guess. So our magnesium is in 2. Oxygen over here in 6. So what do we know about it?
NGO.
Good. Good. Lowest common denominator. Excellent. And then next one we have chromium again, but it's still chromium 3. Boo. Chromium 3, oxide, so we know it's going to be O3. What's the O going to give us?
CR2O3.
Excellent. Cr2O3. Okay. Now, how do y'all feel about those? Not good? So here's your best friend. Your best friend is that little chart you just took a picture of. That's your best friend. Yeah. In fact, if I'm remembering correctly, I believe that I did allow my students to write on your periodic chart the elements, +1, +2, right at the very top of those columns. Do you want to do that?
Yes.
Yeah. Would that be helpful? My chart that I had in college had them on there. It was already on there. I went and wrote them on there, and then I realized, oh, it's already there. You know, so I was like, okay, so I'm not cheating then, I guess. Because that's just a memorization thing. Do y'all understand what I'm asking you to do? At the top of each column, +1, +2, then we have a, is it -3? -4 for carbon, you just have to remember that part of it. And then our minus.
Do you really have to memorize it, or can you just figure it out?
That's what I'm saying, if you write it on the top. If you want to figure it out, go for it.
Okay.
Yeah, not everybody's mind works that way, but some of us are here sitting there going, what? Yeah, so, yeah. If, you know what, it would really helpful if you draw the Lewis structure. Just draw the Lewis structure, you'll see it. You draw a Lewis structure of lithium, it's going to have 1 dot. There it is. It's going to want to get rid of it. It's going to be +1. Because it's going to get rid of 1. So Lewis structure will always help you, especially if you like Lewis structures. I'm not a big fan. Although it's wonderful. It's just visible right there in front of you. Okay, so I think this was a on your own, one of the on your owns in there, but they'll have some of these as your practice problems. Yeah, so do those. Also, I wanted to mention to y'all, talking about if you're struggling, especially if you're struggling a little bit, if you want to try to put together a study group, like I said before, with some of the smart people in the room. Okay, everybody's smart, don't get me wrong. Like I said, I struggled with it, and therefore I found somebody who didn't struggle with it in a class when I was in college, and I made a study group with her. Okay, and so her name's Pam, and she's a doctor today. She's very smart, you know, but she helped me. She ended up being a kind of a natural teacher for me. It was very helpful. And so when I'd sit there and go, she'd see my face, I'd be going, I don't get it. She'd say, okay, try it this way. And she'd give me some new ideas. So also, if you don't have time to form a study group or whatever, then I really do like Khan Academy. I really do. Khan, have you heard of him? Khan Academy. He's fantastic. All you have to put in there is, electron configurations. Explain electron configurations. Find it in Khan Academy. He'll do it. You could watch that with a friend. Y'all could look at it together. This kind of thing. Okay? So, because these actually end up being kind of fun. If you just remember what you're doing, okay, it makes sense that electron's going to go over there, and therefore, and remember the ionic ones are the easy ones. So, not to discourage you at this point. We're going to get harder from here on out, is what I'm saying. In fact, here we are, 4B. All right? 4B, we're going to be looking at Lewis structures some more. And I will tell you, Lewis structures are indeed very helpful. Professor Lewis was trying to make life easier for students. He ended up making, life sort of a bummer because we have to draw the Lewis structures. They're easy breezy when we're looking at ionic compounds. Easy. Okay, we got the dots. We can just move the dots around. But when we're looking at covalent compounds, it gets a little more difficult. Oh, see, we're happy though. We're happy. Yay! Lewis structures. All right, ionic compounds lose or gain electrons to become ions, stick together like a magnet. An ion is an atom that has lost or gained electrons and thus has become electrically charged. I think these are just blanks, yes? And then the process by which an atom turns into an atom is called ionization. That should make sense. It becomes ionized. And then it asks you to do potassium sulfide. I guess I should have made you do it, but we have our sulfur 2 comes down, our K is 1, it comes down, we have K2S. K2S. This was kind of a review, if you will, of part A. So it turns out that ionization, to get rid of or to gain an electron, it needs something. And what it needs is energy. Okay, you can't, it needs to have something to just knock it out of its orbit or pull it out of its orbit. It needs something to cause that process of ionization. And that's called energy. And energy has to come from somewhere. From the first law of thermodynamics, we know that energy is neither created nor destroyed, it only changes form. And so we're going to see, how do we change that form here? How do we do that? Well, we have this energy is going to come from somewhere, it's going to knock that electron out of there, and that electron is going to go do chemistry somewhere. Okay? So we're going to kind of go into a little bit of a parenthesis in your book right here, and then we'll get back to our Lewis structures, okay? And that is looking at ionization energy. Where's that energy coming from? What's it doing? So it turns out, I don't believe these are notes, so you can just listen. It turns out that each atom, depending on where it is on the chart, is going to hold its electrons with a different strength. Some hold them very tightly, some hold them very loosely. You can imagine, for instance, that way over there on the left side of the column with just that one little tiny electron hanging off there, it's going to be really easy to get that electron off of there. Okay, so that's going to be a low ionization energy. It's not going to take much energy to remove that. But one of them that's got like 3 hanging on, boy, you're going to have to really rip those off of there. So it's going to hold on to it a little more strongly. For the atoms that hold them tightly, it takes, tightly, that's right. It takes a lot of energy to take that electron away. For those that hold them loosely, not much energy is required. So the elements on the left side will have a low ionization potential. They're going to want to give up their electrons easily. And the elements to the right side of the chart will have a high ionization potential. They don't want to give them up very easily. That makes sense, doesn't it? Okay. So this brings us to our periodic properties. Ionization potential is the amount of energy needed. How much energy do I need? To the left, not much. To the right, more. In order to take that electron away, it increases from the left to the right of the chart. You might have this blank. Do you? No? Okay. Electronegativity, on the other hand, is the measure of how strongly an atom attracts it. So where the ionization is how much energy is needed to take it, the electronegativity is how much the other atom needs to attract it. Okay? So picture it this way. Chloride is pulling on sodium's electron. Sodium wants to give it up easily, so chloride doesn't have to pull very hard. But if I have something that they're not those two, they're inward, then we're going to have more strong pull from that second atom. So electronegativity is the measure of how strongly the atom attracts extra electrons to itself. Notice electronegativity, it's going to become more negative with electrons. That's what that word is. It's going to become more negative with those electrons. As the electronegativity of an atom increases, its desire to become a negative ion increases, therefore it increases from left to right in the periodic chart. This is all a little bit theoretical, okay? It's just we need to know it. I just don't know that we're going to have to use it that much, okay? The amount of, because we have little cheating, little hints that rather than knowing all this business. The amount of energy needed to take an electron away, that's ionization energy. So here we go. This is how we usually draw it. On your, go right here. The amount of energy needed to take an electron away from an atom.
That's a blank.
This one?
Yes, ma'am. No, the other one.
This one?
Yeah.
So didn't I have that here too? Oh, potential, okay. Ionization energy, the amount of energy needed to take an electron away from an atom. So for sodium and chloride, it's not very high. So we could say a high ionization energy or a low ionization energy. How are we? Good? Okay. All right, so it looks like this. So from the bottom to the top, it increases. From the left to the right, it increases. And from the bottom corner up to the right corner, it increases. Okay, so what does that mean? It's low here. It's high over to the right, okay? Up and to the right is the highest. Okay, so we can say these are held loosely down here. These are held tightly up there. Hold tightly way over there. So you get it? Okay, so loose and then tight, hold. Okay, so let's see an example.
In this experiment, we'll demonstrate two things. First, we'll show that elements within the same group tend to perform the same chemistry. And second, we'll demonstrate the practical consequence to the fact that ionization potential decreases as you progress down the periodic table. Here's the setup. I've got a ceramic dish with water in it, and I'm going to drop in a sample of lithium metal. Now, lithium's a group 1A metal. Look what happens when it hits the water. It starts reacting with the water, doesn't it? You can tell that by the bubbles that are being formed. Those bubbles are hydrogen gas. The chemical reaction is lithium plus water makes lithium hydroxide plus hydrogen. Now you can actually see the hydrogen gas coming off the experiment. It's that smoke. That's the hydrogen gas. Now I'm going to turn up the sound coming from the experiment, and I want you to use what you see and what you hear to get an idea of the violence of the reaction.
We won't be doing this experiment. They won't sell lithium to me. Or sodium, the next one. There it goes.
All right, so you heard some fizzing going on and you saw the reaction complete. Now I want you to compare that with what you're going to see next. In the next part of this demonstration, we're going to do the same reaction, but we're going to use sodium rather than lithium. Now, sodium's a group 1A metal, just like lithium, so you expect essentially the same chemistry to occur. However, it's lower on the periodic chart. That means its ionization potential is lower, and that leads to a rather dramatic difference. Okay, here we go. Okay, so notice that the reaction is essentially the same. We've just replaced lithium with sodium. It's now sodium plus water makes sodium hydroxide plus hydrogen. But notice the difference. The reaction's a lot more violent. It gets even more violent now.
Remember, it's in water, y'all.
What you're seeing now is the hydrogen gas that's being produced in the reaction is burning.
It's catching on
The
fire.
reaction got so hot that it ignited the hydrogen gas. So you're watching a second chemical reaction. Hydrogen plus oxygen makes water.
I'd be burning the church down by now. Yeah.
All right, well, the second
They won't tell
reaction
me
was
that.
certainly more violent, but why? Well, we've got two metals here from the same group, so they're doing essentially the same chemistry, but there's one big difference. Sodium is farther down on the periodic chart than lithium. This means its ionization potential is lower. What does that have to do with anything? Well, in order for this reaction to occur, the metal must give up an electron to become a metal ion. Sodium hydroxide contains the sodium +1 ion. Lithium hydroxide contains the lithium +1 ion. So each of these metals is giving up its electron in order to perform this reaction. Well, since sodium has a lower ionization potential, it gives its electron up more easily. This means it can react more quickly with the water. And that's the difference you're seeing in the reactions. The second reaction is quicker because the sodium gives up its electron more easily than the lithium does.
That makes sense? It's good, yeah? So it's holding on to it more loosely. All right, a chemist needs to find an element that readily gives up an electron. Which of the following would suit her needs best? So look at your chart. Would calcium, whatever AS is that astatine? No, that's arsenic, whichever that is. Arsenic or bromine. So check out the chart. Remember our arrow. Think of that arrow going and. So which one is holding on to its electron the most loose?
Calcium?
Y'all agree?
I agree.
You do agree? Calcium? Okay. All are on the same row, but calcium is to the left of the others. Since ionization increases from left to right, calcium has the lowest ionization energy, so it gives up its electrons more easily. Do you get it? Not bad, right? Okay. What question?
Oh, I was wondering if that was it.
That's it. That's all I'm asking. Yeah. Which one of these, aluminum, In, or B boron, holds its electron the tightest? The tightest.
Indium?
Is that what it's called? Indium, In. They're all on the same column. Boron is above the others, and since ionization it decreases from the top to the bottom, boron actually has the highest ionization energy. Therefore, boron holds its electrons the tightest. Remember that arrow goes blup, blup, blup. Does it make sense? Okay, y'all are happy with that? Which element has the highest ionization energy of all? Think about those arrows. Which one has the highest ionization of all of them?
Helium.
Check it out. It's helium. Yeah. Remember, it doesn't want to do any chemistry at all. It's like, everybody back off. Yeah. Okay, our electronegativity is a little different. Instead of, giving up or whatever, it's pulling. Okay, so the electronegativity is the measure of how strongly an atom attracts the electron to itself. It's like pulling. Okay, so just like tug of war. Our picture here is showing tug of war. Who's the strongest is going to pull it. So we're going to look at our electronegativity values on the periodic chart as well. So the way that you saw how the ionization has those arrows, we're going to have similar here. And look at the arrows. Up, over, and up again. Is it the same? It is. Okay? It's the same. So it increases over here, decreases down here.
Can you go back one?
Here?
Yeah.
The measure of how strong an atom attracts. I thought it was just a little blank for attracts. No, it's the whole thing?
Yeah.
It's a bummer when you get up in the upper level high school classes, right? Got to do lots more writing. So remember electronegativity, they're becoming more negative according to how many electrons they've just pulled off of something. They just ripped off something. Okay, so if this is what it looks like here, which one of them wants the electron the most? Okay, which one of these wants the electron the most? All right, so our calcium is all the way over here. Oh, look, they're in the same row, yes? Potassium, calcium, arsenic, and selenium. Okay, so which one is going to want it the most?
Selenium?
Yep, it's selenium. Now, I want you to notice on this particular chart, and in the chart I had in college, had a lot more information than y'all's has on there. Look at this number below there. See if adult potassium, it says 0.8. Calcium says 1. It's a bigger number. And then our arsenic over here, 2, and our selenium, 2.4. That's actually its electronegativity number. So notice the biggest electronegativity number was indeed selenium. See? So on a chart you had in college, your chart will give you all of that information. You won't have these questions, which one's the most electronegative, because it already is, the information's already there. But for y'all, you just need to understand that fundamental truth about these. Remember, we're just looking at changing those electrons around. And so this one's going to pull it the most over here to this side. Now this is, to me, the strangest part of the whole deal is atomic radius. You would think if something has more protons in the middle of it, it's going to get bigger, 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 bigger. Its radius of the atom is going to get bigger and bigger. It's not exactly true. So what is the atomic radius? It's the average radius of an atom, which of course is going to be very, 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 very small. Okay, but it actually decreases as you move across the chart from left to right and increases as you move down. And the reason is, your book will explain it a little better than I can, but the idea is that you're packing those protons in there. They'll actually pack closer together. It's like we're going to squish them closer together, which actually brings down the overall radius of the atom. Does this mean anything to us? Not really. Okay, it's not really important for us right now, but you can see it kind of looks like this, and this way, I think, like that. So this is the summary right here, that the atomic radius as it goes to the right will decrease where everything else will increase. And as it goes down, the atomic radius will increase while the other things decrease, the ionization, electronegativity. So this is a nice little summary slide right here to tell you what's going on. So I just have one question about which element has the largest atomic radius of all of these. We're back in our group. Calcium, arsenic, potassium. So the same group we were looking at before.
Potassium.
Sure looks like it. Yeah, there you go. All right. Get it? I'm not too, yeah, whatever. Now, these guys are super, 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 super important. Okay? You need to write these in your little boxes there, and then you need to never, ever forget them in your whole life.
Oh.
Put a star by it.
Got it.
These guys are called homonuclear diatomics, and what it means is when they're out looking for someone to give an electron to them or to share an electron with them, oftentimes they will do it with themselves. Remember I said that about fluorine? It will mix together with itself. So these guys are going to do this all the time. In fact, when we see them by themselves, we will never, for instance, we will never write down hydrogen with just an H. We will always write down hydrogen with an H2. Because it's a homonuclear diatomic, it hangs around with itself. Think of them like twins. Let's think of them like, Siamese twins. They're stuck together. Okay? When they're by themselves, they have a buddy. They have their twin with them, okay? That doesn't mean that I have to have two H's in every single molecule that I have. No, not with molecules, by themselves. Does that make sense? Mm-hmm. So hydrogen by itself is going to be an H2. Oxygen by itself is going to be an O2. Nitrogen, N2. All of column 7A except for number 117. What's in column 7A? Fluorine, chlorine, bromine, iodine, and astatine are all going to be F2, Cl2, Br2, I2, and At2. 117, Tennessinian. Somebody from Tennessee named that one, I guess. Don't pay attention to that guy. There they are. Fluorine, chlorine, bromine, iodine, astatine. And it has to do with the stability of the atom. They join up, they hold on to each other, and they're going to end up sharing electrons there. Which is going to bring us to our Lewis structures for covalence here in just a second. Yikes. All right, we got it. Does everybody have their homonuclear diatomics written in those boxes? That's the number one thing you need to have. Okay? And now we got to go apply. I don't even know if we're going to apply this right now. You will need this for future modules for the rest of the year. You'll need to remember this. It's not hard. Remember group 7 plus hydrogen, oxygen, nitrogen. That's it. Not hard. We got to get through the rest of the lecture, y'all. All right. So, Lewis structures for covalent compounds. Okay, these covalent, the difference with the bond here is there's going to be a sharing of electrons that hold them together a little more strongly. So, a covalent bond is going to be a strong bond. They're going to share the electrons to form molecules. Typically, they're all nonmetals. Ionic compounds give and take electrons to form molecules. Covalent will share. All right, so take a look here. This is a Lewis structure. Now, one thing you need to know, we're going to watch a video here in just a second. It's going to be it's called Lewis Structures Made Easy. That's the kind I like right there. What you need to know is that when I have two electrons that are being shared, we'll draw a line right there. So this line right here between the H and the C is representing 2 electrons. How many did hydrogen contribute? 1. Hydrogen only has 1. And therefore, carbon is contributing the other one. Something I need you to understand that's going on here is that hydrogen thinks it's got 2. So is hydrogen happy? Yes. Chlorine, on the other hand, we're going to count 1, 2, 3, 4, 5, 6, 7, 8. Carbon says, whoa, looky there. I have 8. I'm happy. Hydrogen says, I have 2. I'm happy. And oxygen has, this counts for 2. This line counts for 2. 1, 2, 3, 4, 5, 6, 7, 8. Now, do you see how there's sharing going on here? Now, how does it exactly work? Remember, electrons are spinning in orbits. So at some point in time, they're all spinning around carbon. At some point in time, 2 are spinning around each of the hydrogens. At some point in time, 8 are spinning around oxygen. Okay, so they're sort of like, playing a little game here. And everybody's happy. So they average out that everybody's got their 8 or their 2 for hydrogen. Okay? So this next video I'm going to show you will explain this so beautifully. Although you're going to see a little remnant of this writing from here. Okay. I like this guy. Don't fall asleep.
Welcome to Lewis Diagrams Made Easy with Ket's book. Today we're going to learn how to draw Lewis diagrams for atoms and simple molecules. But before we begin, let's start with a question. How many valence electrons does chlorine have? In order to answer that question, we need to look at the periodic table. Remember that within any given column, all the elements have the same number of valence electrons. To get that number, all we need to do is count the columns starting from the left. Skip the transition metals and remember that the only exception to this is helium, which has only 2 valence electrons, not 8. Now, find chlorine in the periodic table. Remember that its symbol is Cl. See it in the 7th column? That tells us that it has 7 valence electrons. Knowing the number of valence electrons an element has is critical, and in Lewis diagrams we use dots to represent valence electrons. So, the Lewis diagram of chlorine is the symbol Cl with 7 dots around it. When you draw the dots, don't just put them anywhere. Instead, imagine a square around the element symbol. The dots should be neatly drawn on the 4 sides of the square with no more than 2 dots on any side. Practice drawing Lewis diagrams of a few elements just to make sure you've got it. This is the Lewis diagram of hydrogen, which has only 1 valence electron. This is carbon, which has 4 valence electrons. And this is oxygen, which has 6 valence electrons. Where you put the dots, it doesn't really matter as long as you neatly draw them along the sides of an imaginary square and never put more than 2 dots on one side.
And don't leave a place empty.
Lewis diagrams are often used to represent covalent bonding in molecules and ions. In covalent bonding, atoms share valence electrons in order to get a full octet, or duet. That is, every non-metal element wants 8 valence electrons, except for hydrogen, which only wants 2 valence electrons. The simplest molecule possible is that of hydrogen, H2. A hydrogen atom has 1 valence electron, but it wants to have 2. So in order to satisfy its desire for another electron, 2 hydrogen atoms will share their electrons with each other. And the crazy thing is that in the wonderful world of atoms, the shared electrons are counted as owned by both atoms. That means that both hydrogen atoms are happy because they both satisfy the octet rule. Now, we normally draw hydrogen and other molecules like this with lines to represent shared electrons and dots only for non-bonding electrons. These 2 diagrams of a hydrogen molecule are equivalent because one line, which is a single bond, represents 2 shared electrons. In the same way, 2 lines between atoms would be a double bond and would be the sharing of 4 electrons. An example of a molecule with a double bond is oxygen, which looks like this. Notice that in this Lewis diagram, both oxygen atoms have 8 valence electrons, 4 from the double bond and 4 from the lone pairs of electrons. By the way, 2 dots together are called a lone pair of electrons. Some molecules contain triple bonds, which we write using 3 lines that represent the sharing of 6 electrons. An example of a molecule with a triple bond is nitrogen, which looks like this. Once again, notice that both nitrogen atoms have 8 valence electrons, 6 from the triple bond and 2 from the lone pair of electrons. Okay, how do you actually draw the Lewis diagram of a molecule? Let's start with water, H2O. There are 5 important steps that you need to follow when drawing the Lewis diagram of a molecule. First, count all of the valence electrons in the molecule. For water, each hydrogen has 1 electron, and we multiply that by 2 because there are 2 hydrogens in the molecule. The oxygen has 6 valence electrons. Add those all up, and we have a total of 8 valence electrons for the water molecule. Step 2, determine the central atom. The central atom is the one that all the other atoms will be bonded to. It is usually the element that there is only one of. In the case of H2O, because there are 2 hydrogens and only 1 oxygen, we choose oxygen as the central atom and write it in the middle. Step 3, draw single bonds to the central atom. Step 4, put all of the remaining valence electrons on atoms as lone pairs. For H2O, we start with 8 valence electrons. We have used 4 electrons for the 2 single bonds, so that leaves 4 more electrons left over. We put all 4 of these remaining electrons on oxygen instead of hydrogen because hydrogen is already happy with 2 valence electrons. Remember, never give hydrogen more than 2 valence electrons. Everyone else wants 8 valence electrons, but hydrogen only wants 2. Step 5. Turn lone pairs into double or triple bonds to give every atom an octet or duet for hydrogen. Pause the video and see if all the atoms in our H2O are happy.
Yeah.
Because each hydrogen has 2 electrons and the oxygen has 8 electrons, everyone is happy, and there is no need for double or triple bonds, which means that our Lewis diagram of water is now complete. Alright, let's try one more example just to make sure that we've got this. Draw the Lewis diagram of sulfur trioxide. Once again, the first step is to count all the valence electrons. There is 1 sulfur with 6 valence electrons, and there are 3 oxygens with 6 valence electrons each. 6 times 3 gives us 18 valence electrons for the 3 oxygens. The total would be 6 plus 18, which equals 24 valence electrons. Step 2, determine the central atom. This time, sulfur is the central atom because there is only 1 sulfur in the molecule. We write sulfur in the middle with the 3 oxygen atoms all around it. Step 3, draw single bonds to the central atom. Step 4, we started with 24 valence electrons, and we have used 6 electrons to make the 3 single bonds. This means that we have 24 minus 6, or 18 valence electrons remaining. We now put those remaining 18 valence electrons on atoms as lone pairs. Count by 2s when adding them. 2, 4, 6, 8, 10, 12, 14, 16, and 18 valence electrons. That's it. We've now used up all of our valence electrons. Step 5. First pause the video and check to see if any atom does not have an octet or duet.
So I did pause it here. So notice I have 1, 2, 3, 4, 5, 6, 7, 8. 8, but sulfur, 1,
That's
2, 3,
right.
4,
The
5,
sulfur
6.
is unhappy
It's not
because
happy.
it only has 6 valence electrons. So what can we do to make it happy? We cannot just give it more electrons since we don't have any more. Instead, one of the oxygen atoms can take one of its lone pairs and share those 2 electrons with sulfur in another bond. The double bond between oxygen and sulfur now makes every atom happy with 8 valence electrons. Be sure to
What do you think? I really like the way this guy explained it. I will tell you this, his little rules over here that he put over here are to me more helpful than the rules in your book. I like these better, okay? Also, notice that if I have sulfur trioxide, I didn't do something like this. I didn't write the sulfur and the oxygen and another oxygen. No. Always have a central atom and the other things are going to hang off of it, okay? All right, don't give me something weird like that. unless we're looking at something like a hydrocarbon chain or something with a bunch of carbons. That carbon's an exception to that rule. When I'm asking you to draw something, it's going to end up with something in the center and stuff hanging off of it. All right, so we have some examples here. The covalent compound Lewis structures for these. So we have fluorine, which is a homonuclear diatomic, and we have CCl4. All right, CCl4 right here. So that's, I can't remember the name of that. All right, so we're going to start with fluorine, and we're going to see what group is it in. So our first thing in our rules, we're going to find how many valence electrons does it have? 7. And so it's going to try to complete that. So we have 7 and 7, and what they're going to do is they're going to put that guy and that guy together, and we're going to have F2 with a single bond. So let's see. This counts for 2, 3, 4, 5, 6, 7, 8. So that fluorine's happy. Shared. 1, 2, 3, 4, 5, 6, 7, 8. That fluorine's happy. So just an F-F. So all you're doing is putting a little dash between the F's on your book. Single bond. I love single bonds. Double and triple bonds get a little bit scary sometimes. And then our CCl4 is just going to end up looking like this. Let's check it out. Our carbon's going to have 2, 4, 6, 8 because that line counts for 2. Carbon is happy. This is one of the really special things about carbon. It's got 4 binding spots right there. It also likes to link to itself a lot. That's when we'll end up with a long chain. With my Cl, I've got 2 for the line, 3, 4, 5, 6, 7, 8 for the dots. So each one of my fluorines is happy. So those Lewis structures are nice. Nice and neat. So when that sulfur trioxide comes in, that gets you. That can actually go a couple different ways as well. Okay, so Lewis structures for covalent compounds. A shared pair of valence electrons that hold atoms together is in a covalent compound. They share them. We've already said this, right? And these give and take. That's just a review right there. So here are the steps.
We have a blank to fill in about the covalent bonds.
Right here, a shared pair of valence electrons that holds atoms together in covalent compounds. Which one? Share? Covalent molecules share?
I think it's the top one. Covalent bond.
Okay, so that's what that bond is, that shared pair of electrons. That line is called a covalent bond. And since they're sharing, you can see that's going to be a little stronger bond than our ionic bond, which is just being held together by charges, like a magnet. This is going to be a stronger bond. They're sort of gripped to each other. So tearing these bonds apart is going to be a little more difficult. And why would we want to tear these bonds apart? To do chemistry. Yeah, your body's doing it right now, especially if you ate breakfast. Your body's tearing up all that breakfast you ate, tearing those bonds apart to give you some energy. So you can think and know this chemistry and love it. I can tell y'all are loving chemistry. All right, are we good, everyone? All right. These are the 3 steps for Lewis structures of covalent compounds that you find in your book. All right, so notice what the first step is. It's different from what the guy said in the video who said Lewis structures made easy, right? It says here to write the Lewis structure out. All he did was count the valence electrons. Do you see how that's the same thing? Because if I'm writing a Lewis structure, what are my dots? Those are my valence electrons. So you can draw it if you want to. If you're a visual learner, draw it and draw those dots next to it. Otherwise, just look at the chart and see I've got 2, and I can add them together and just do a little math. Which one do you think would be easier for you? You like the dots? Yeah, dots are good. All right. Now, notice also what this is different as well. This step to me was a little esoteric. Do you know this word? Esoteric, mysterious to me. Okay, because it says here, put the atom with the most unpaired electrons in the center. What did the guy in the video say? He said, put the one that's by itself. All right? I will tell you that sometimes that doesn't work. For the vast majority of time, it does work to put that one that's by itself in the middle, but not every time. So this one is a little more accurate, a little more focused in. So the one with the most unpaired electrons, I got one hanging off by itself. I'm going to put it in the center. But in my mind, at this point, I'll just start with putting that one that's by itself in the center and see if that's going to work for us. Okay? So that video, I really liked how he put that. If there are more than one of those atoms, put them all in the center linked together. That happens with our carbons. only with our carbons, okay? Well, for y'all right now. Try to arrange the other atoms around the center atom, making sure they have 8 electrons except for hydrogen, which is going to have 2. All right, so here we go. What is the Lewis structure for a water molecule? This is 4.5. Let's watch it.
In this example, we're going to draw a Lewis structure for the covalent compound H2O. Now remember, covalent compounds share electrons. Ionic compounds give and take electrons. So electrons in this compound are going to be shared. All right, the first thing we have to do is figure out how many valence electrons are in each element. H2O has H, and there H is in the periodic chart, and O, and there O is on the periodic chart. All right, H is in group 1A, so it has 1 valence electron. We represent that by putting 1 dot to the right of the H. There are 2 H's in H2O, however, so we have to have 2 H's, each with its own valence electron. So those are the H's we have to work with. Oxygen is in group 6A. That means it has 6 valence electrons. We put those on one at a time, starting from the right, going to the bottom, to the left, and to the top, and now we start doubling up, right and bottom. That's 6 electrons. So these are the elements that we have to play with. You can think about Lewis structures like puzzles. Most elements behave according to the octet rule. That means they want 8 valence electrons. Some elements are exceptions to that rule, and hydrogen is one of those exceptions. It doesn't want 8 valence electrons, it only wants 2. All right, now in covalent compounds, the electrons are shared. So we have to figure out a way to get hydrogen to share 2 electrons, and oxygen to get a total of 8 electrons, including the ones it's sharing. How do we do that? Well, the first technique is to take the atom with the most unpaired electrons and put it in the center of the molecule and try to hang all of the other atoms off that central atom. Well, oxygen has 6 electrons. 4 of them are paired, but 2 of them are unpaired. Hydrogen has only 1 unpaired electron. So oxygen is the atom that's going to go in the center, and we're going to try and hang the hydrogens off the oxygen. Well, it's not hard to see what has to happen here. Oxygen wants 8 electrons. It currently has 6. It has 2 open spaces. Here's one, here's the other. So all we need to do is get the hydrogens to take their electrons and fill in that empty space. Look what happens when we do that. An atom thinks it owns any electrons that are either next to it or between it and the very next atom. So look at the hydrogens. They each think they own 2 electrons because there are 2 electrons between them and the oxygen. Look at the oxygen. It thinks it owns 8 electrons. 4 of the electrons it owns outright. The other 4 are between it and one of the hydrogens. So in the end, the oxygen thinks it owns 8 electrons. The hydrogens think they own 2 electrons. So the oxygens and the hydrogens both have their ideal electron configurations. The electrons that exist between each hydrogen atom and the oxygen atom are shared electrons. The hydrogens think they own those electrons. The oxygen thinks it owns those electrons. So the electrons are shared. Shared electrons are covalent chemical bonds. We typically symbolize that with a stick rather than a pair of dots to emphasize that this is a bond linking the 2 atoms. So to finish off the Lewis structure then, we take each shared pair of electrons and replace them with a stick. This is our Lewis structure for water. Now I want to make a quick
those
point
2
about...
dots. I'm going to move on because we got to go. All right, so we have more, that was easy. So we have more complex ones, and so we're going to be looking at carbon dioxide now, and then for HCN and... That was easy one, yeah.
In this example, we're going to do 2 more Lewis structures, which are a little more complicated than the one we did before. The first is CO2. CO2 has carbon, there's carbon, and oxygen, there's oxygen. Now carbon's in group 4A. That means it has 4 dots around it. Oxygen is in group 6A. That means it has 6 dots around it. There are 2 oxygens in CO2 though, so we got to have 2 oxygens here. Alright, so those are the elements I have to play with. Now the first thing we do is we look for the atom that has the most unpaired electrons. That's carbon. Carbon has 4 unpaired electrons, oxygen has only 2. So carbon is the central atom. We therefore will have to try and hang the oxygens off of the carbon. Now look, the carbon has 4 empty spaces. That's what those 4 squares are. Each of those empty spaces would like to accept an electron. I don't see how I can get 4 electrons into those 4 empty spaces, but I do see how I can get 2 electrons into 2 of them. Each of those oxygens can come up to the carbon and put 1 of their unpaired electrons into a space. All right, that's what we have so far. None of these atoms have their ideal electron configuration
And
yet.
neither of them.
The oxygen has only 7 electrons. It wants 8. So I'll put little red squares indicating an empty space on the oxygen. The carbon has 6 electrons. It wants 8. So I'll put blue squares representing the empty spaces on the carbon. How do we get these atoms to each think they have 8 electrons? What we have to do is move the electrons around. Remember, an atom thinks it owns any electrons that appear between it and the next atom. So if I can get these electrons to move around a bit so that they appear in between the carbon and one of the oxygens, then things can happen. Look at the carbon and look at the oxygen that appears to its immediate right. Both of them have an electron sitting on top. I'm going to move those electrons down in between the carbon and the oxygen. Now look what happens. There are now 4 electrons between the carbon and the oxygen. Both the carbon and the oxygen think they own those electrons. All right, let's do the same thing to the other 2 unpaired electrons. We'll move them in between the carbon and the oxygen right below it. Now there are 4 electrons between the carbon and that oxygen. Once again, both the carbon and the oxygen think they own those electrons. So look at what carbon thinks it owns. It thinks it owns all electrons either next to it or in between it and the next atom. So if I draw a square around all the electrons the carbon thinks it owns 8 electrons. Look at the oxygen. If I draw a square around all the electrons that the oxygen thinks it owns, it also thinks it owns 8 electrons. It owns 4 of them outright. 4 of them are between it and the carbon. So that's a total of 8. Let's look at the other oxygen. Once again, it owns 4 electrons outright, but it also thinks it owns those 4 between it and the carbon. So it thinks it has a total of 8 as well. So all of the atoms now have 8 electrons around them. They all satisfy the octet rule. Now remember, shared electrons are covalent bonds. When we have 1 pair of shared electrons, we represent that with 1 stick. When we have 2 pairs of shared electrons, we represent that with 2 sticks, and we call that a double bond. So in each case, we're going to take the 4 shared electrons and replace them with double bonds. So in this
Okay,
Lewis
y'all got
structure, the carbon,
Okay, I'm going to move on. HCN is going to end up with a triple bond in there. Okay, so look at that in your book, but we have to go on. The application of this, of the Lewis structures right here, are something we deal with in our electromagnetic spectrum, namely in the atmosphere. So here's what you're writing down in those last blanks on your book right there, is that N2, which look has triple bonds right here, plus those 2 dots right there, breaks down harmful gamma rays. Are you just writing N2 there? O2 breaks down harmful X-rays coming from the sun, and O3, called ozone, is breaking down harmful ultraviolet rays. And you can see kind of a complicated Lewis structure here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then over there. So you see we have a double bond in there in our ozone. And that high energy bond, if you got 1 bond is pretty strong, 2 bonds is even stronger, triple bond is very strong. Okay, because all those are being shared right there in the middle. All right, and I believe that is it for your notes. Next week, you're going to bring a study guide, and we're going to have a quiz. 2 of you have a quiz from last week that you missed. I've got it right here somewhere. And then I have a quiz to hand to those of you who came a little late. And so there's our